Problem 12. There's a sketch of two batteries in parallel. It says, as shown in the sketch to the right, two AA batteries are connected to a 150 ohm resistor. The power dissipated by the resistor is something. In some versions of the test, AA batteries were not given, and you were just given a voltage source, so you needed to know that the AA battery is 1.5 volts. Let's take this as known. The power dissipated by the resistor. So the question here is, what happens? How do these batteries work? Well, they're connected in parallel, so it doesn't matter. The voltage here to here, this voltage difference, is the same as the voltage here to here, and it's the same as the voltage here to here. So if the voltage is 1.5 volts here, the voltage across the resistor is 1.5. So the power dissipated by the resistor is equal to voltage divided by voltage squared divided by the resistance value. That just comes from our definition of power as VI, and we substitute in Ohm's law. So this is simply equal to 1.5, which is our voltage, squared divided by the resistance, 150 ohms. And we do the computation. So we see there's a nice 1.5 factor appearing in both of these, 1.5 squared. So 1.5 squared divided by 150 is 0.015 watts. Number 13. If a current of 40 milliamps leaves the power source, then the resistance R is closest to. So we know I equals 40 milliamps, and this is the current that leaves the power source, I. Then the resistance. Well, we know the voltage across this resistor, we know the current through it. We have V equals IR. Ohm's law, we solve for R because that's the only unknown here. So divide through by I, V over I, and it's equal to 5 volts. What you need to know is, what is a milliamp? A milliamp is 1,000th of an amp, or 1 amp equals 1,000 milliamps. So this is 0.04 amps, and we can just do the calculation here in our head. Multiply numerator and denominator by 100, it's equal to 500 over 4, or 125. Number 14. The power consumed by the 3 ohm resistor is closest to. So we want to know the power in this resistor. If we knew the current through that resistor, we could do I squared R, or if we knew the voltage across that resistor, we could do V squared divided by R. The current is probably the easiest. We have a voltage source, we have an equivalent resistance here. So this voltage source is equal to the I total current times the equivalent resistance of the circuit. The equivalent resistance is just these two resistors in series. So we can solve for I total as V source, in this case 5 volts, divided by the equivalent resistance, that's just R1 plus R2. If this is R1 and this is R2, they're in series. This is equal to 5 volts divided by 2 plus 3, or 5 ohms, or 1 amp. So if the current is 1 amp, we're still looking for the power. So the power in this resistor here is equal to I squared R, 1 amp squared times the resistance, 3 ohms. So it's 1 times 3. Number 15. In the circuit to the right, these 4 resistor values all have the same number, same value, 100 ohms. V sub S, the voltage supply, is 5 volts. What is the total current leaving the voltage supply? Show the formulas and intermediate calculations necessary to obtain your solution. Note that different versions of the exam had different R values. So we have to find the current leaving the voltage source, which is V sub S here. So have to organize this into a way that this looks familiar. So the first step is to identify, or to rearrange this so that we can identify the series and parallel paths. Notice that this loop here is in parallel, so we identify these nodes here. This resistor is in parallel with these guys, so I could take this wire and fold it around so that it looked something like this. I won't bother labeling the resistance values. So I could take it and fold it around so that it looked like this instead. But these are all the same, so I could represent this as so this guy is in parallel like this. So my new circuit is simpler. I've got R1. I'm going to redraw this over here to make it a bit neater. My circuit is equivalent to this. Voltage supply, R1. This first resistor, R2 and R3 are clearly in series, and they're downstream of R1, and they return to the negative terminal on the voltage supply, and R4 is in parallel with that whole bunch. Okay, so I worked it sort of in a scrap mode here, but this is now my circuit. So I want to know the total current leaving this voltage supply here, and basically if I reduce this to a single equivalent resistor, I apply Ohm's law to this entire circuit then with a single equivalent resistance here, and I'm done. So let's combine these guys. I'll go through it slowly here. R1, we can replace these two and call it R23. R4, where R23 is these two in parallel, and that's equal to 1 over R2 plus 1 over R3. Okay, now combine these two in series, call it R1, R2, R123, and then this guy is still in parallel. R4 is in parallel with this. R123 is equal to R1 plus R23, and then I could copy that over, and simply these two are in parallel. I'll reduce it again one last time. The equivalent resistance is equal to these two in parallel, 1 over R123 plus 1 over R4. And the rest is pretty much just computation. So I'm going to use the values of 100 in all of these computations here. So this guy is equal to 1 over 100 ohms plus 1 over 100 ohms. That's equal to 1 over 2 over 100 ohms. So invert that, and that's equal to 100 ohms. Oops, sorry. That's equal to 100 ohms over 2, or 50 ohms. So R23 is that. R1 plus R23 then is equal to 100 ohms plus R23 is 50 ohms. That's 150 ohms. And the equivalent resistance 1 over R123 plus 1 over R14, or R4 is 1 divided by 1 over 150 ohms plus 1 over R4, which is 100 ohms. We could multiply this by 2 over 2 to get 100ths and 3 over 3. So this is equivalent to 2 over 2 over 300 ohms plus this is 3 over 300 ohms. Now we can combine these two. I get 1 over, this is 5 over 300. So the answer here is the reverse of that. This is 300 ohms over 5, or 60 ohms. So, don't even need a calculator. Now, finally, we have VS is equal to I total times R equivalent. So the total current we're still trying to solve for. I total is equal to V sub S over REQ. REQ we've just found as 60. This is equal to 5 volts over 60 ohms. That goes into it 12 times. That's 1/12, which is something less than 0.1. 5 volts divided by 60 is equal to 0.833. So I total equals 0.0833 amps. Now, you can repeat this calculation with different values of R1s and R2s and R3s, but the process is the same.